For section 2.4, we're going to solve systems, and the first way we're going to learn about is to solve them by graphing. We'll learn other methods like substitution, elimination. Ideally, you will learn what is the best method in a given situation. But let's explore graphing first. Okay, there are three different possibilities when we're graphing these two lines. A system is just a set of two or more equations with the same variables. So if we graph it, they could just cross at one single point. So they have different slopes. There's going to be one solution. We call that consistent and independent. Consistent because there's at least one solution, and independent because it has exactly one solution. I kind of look at these as independent lines. They can be each graph themselves independent of the other. Another possibility, it's hard to see here, is actually there's two lines, one right on top of the other. They're actually the identical lines or the same line. They have the same slope, same y-intercept. Therefore, there's infinitely many solutions. They cross at a whole bunch of different points, infinite amount of points. We call that consistent because it still has at least one solution, right? So it's consistent. And we call it dependent because there are infinitely many solutions. Basically, you could look at it as like a set of twins. If these are identical twins, they're dependent on each other, and they look alike, kind of thing. Here, if we have two separate siblings, then they are independent. Okay? The last option is if we have lines that are parallel, so they would never cross. That's why there's no solutions. They would have the same slope but different y-intercepts. So they start in different positions, but they have the same slope, the same rate of change, so they'll never cross. We call this system just straight up inconsistent. You don't need to worry about the dependent or independent. It's just straight up, it is inconsistent when there's no answer. So can we classify a system? Can we basically know how many solutions it has without having to even graph it or solve it? Really what you want to do though is just compare their slopes and y-intercepts. So let's get them into the right format. So if you look at this first equation, this 2y equals 6x minus 14, I want to divide everything by 2 and I get y by itself. So I got my first equation, has a slope of 3 and a y-intercept of -7. For the next one, okay, I'm going to have to minus the 3x first to get y by itself. You guys have done this before. Now I got this equation, but there's a -1 here, so I'm going to divide everything by -1. So now I have this equation. If you look at it at the start, they look completely different, but when you actually rearrange them, you realize, oh wait, they have the same slope, the same y-intercept, so they're really the same line. So therefore our answer has to be there are infinitely many solutions. You could also say it's consistent and dependent. They depend on each other because they're the exact same. Let's try that again. And feel free to pause and try it yourself. For the first equation, you're going to have to move the 3x first. Then we're going to divide by -2. You may not always get whole number answers, and just leave it like this. We don't actually have to graph it. If I was graphing it, I might want to change this y-intercept into a decimal so I know where to start, but I'll just go up 3 over 2. Let's compare it to the other one. On this one, you just need to divide by 4. Divided by 4, I just left the 9 over 4. I put that second because that's the y-intercept here. The -6 over 4, if you reduce it, just becomes -3 over 2. So if you look at this one here, it's like, wait a second, they almost have the same slope, but they are different, positive versus negative, different y-intercepts. So these are just two, different slopes, different y-intercepts. These are just two random lines that are going to cross somewhere. So there's only going to be one solution. We'd say this is one solution, or we could say it's consistent and independent. They're independent, separate lines here. All right, so let's actually graph it and figure this all out. Again, you may have to rearrange these equations. So that's what I'm doing off to the side here. I took the first equation, I rearranged it, got y by itself, so that's easier to graph. There's other ways to graph too, finding intercepts and all that good stuff. You do you. This is also nice to compare. This here, if you move the x over, now I can compare, I could see like, okay, they're definitely different slopes, different y-intercepts, so they're gonna cross somewhere. I just gotta find it. The first graph starts at -3, goes up 5 over 1, up 5 over 1, draw your line. The second line starts at 5. There's just a slope here of 1, so it goes up 1 over 1, up 1 over 1. You want to try to plot as many points as you can, especially on the first one you graph, because I don't know where they're going to cross. Now that I see I plotted the second one, I go up 1 over 1, I can see, oh yep, they're crossing right over here. I don't even have to worry necessarily about going backwards, unless I just want to get a more accurate picture. I can just draw the line and find this point, which should be at 2, 7. Don't forget, you can actually plug that in. That's an x, that's a y. Plug in 2 for x, 7 for y, and you should see that it works for both of these. They do make equal, satisfy the equation. Feel free to pause and try the next three yourself. This one here, you're just going to do the same stuff. Get y by itself, rearrange this, get y by itself, and then again, I see different slopes, different y-intercepts, and all that good stuff. So they're going to have one single point. So the first one starts at -3, goes down 7 over 1, or I could go up 7 to the left 1. This one starts at 6 and goes up 2 over 1, up 2 over 1, positive slope, but I actually need to go down and to the left to work it backwards to find where they cross. Should be, in this case, -1, 4. All right, for our last example here of graphing line before we get into a word problem, again, I'm just rearranging both of these. So I rearranged the first equation, rearranged the second equation. I just reduced the fraction 21 over -6, reduced it to -7 halves. And let's see what we got here. Wait a second. I can already see these have the same exact slope, but different y-intercepts, different starting points. So yeah, one starts at -4 and goes down 7 over 2, or up and to the left 2 there. This one starts at 8 and goes down 7 over 2. So they're parallel. They're never going to cross. So we would say there is no solution. It is inconsistent. All right. Lots of word problem, just comparing two things. So now we can start to solve problems that involve, two different situations. So in one situation, we are driving an electric car, so it costs 0.036 per mile. That's where this comes from. That's your slope. But it costs you $29,000 to buy the car. The other one is 0.08 per mile, but it costs $19,000 to buy the car. And actually, this is something to look at. Electric cars do cost more to purchase them. You can see, like here, this is cost a lot less, but you can see that the gasoline car will cost more per gallon of gas and whatever mile to drive or whatever they're comparing here. So as technology gets better, hopefully we'll see these prices kind of change and shift, and maybe hopefully be maybe better to buy an electric car. But let's see what happens here. They say to graph it. Luckily, they've already graphed it for us because these numbers are quite large. We might use a program like Desmos to help us graph these. They've graphed it for us here. This one starts at 29,000. Notice they're doing this in thousands of dollars and thousands of miles here. And they graphed it, and that was very nice of them. So we're just basically estimating where this crosses right here. So I don't know, this looks like about, okay, more than 210. I mean, I have the answer key from the book, so I know that was like 225 was right around here. And then it's up at 37. So what does that really mean in thousands is that after driving 225,000 miles, the cost of owning each car will be the same. So you can see here, the cost would be around $37,000, what it's going to cost you to go those 225,000 miles. You can see the gasoline car is always lower, always cheaper until we get to this point. Then the gasoline car becomes more expensive and the electric car becomes cheaper. Obviously, depending on the car and the gas prices and all that stuff, this would change in the real world. So I'm hopeful that one day we'll have a better deal with electric cars and they would become more affordable. Right now, it's kind of still maybe, according to this graph, the gasoline cars are still a little bit better right now, maybe because they're cheaper to buy. All right, bring questions to class.